Hello friends, welcome you all for this video lecture. In this video lecture, we are going to look at solving a problem on Brayton cycle. So let us get into the video. First, let us look at the question. We will try to understand the question. Then we will write down the data given, and eventually we will find out the required parameters one by one. Right. Uh, First, in this problem, they have given uh, that in a gas turbine plant working on the Brayton cycle. So first we need to identify the kind of cycle, because in thermodynamics we are studying about different types of cycle. So we need to identify which cycle is given. So in this problem, it is quite easier to find out because the name of the cycle is directly given in the question. Then it is given that the air at the inlet is at 300 Kelvin and 0.1 MPa. So that means at the inlet means at the beginning of the cycle. Normally in the Brayton cycle, the beginning process is the compression process, which is taken as 1 to 2. So therefore, at the beginning state, the temperature is T1. So therefore, I have written T1 here equal to 300 Kelvin, and the pressure at the beginning or at the inlet is 0.1 MPa. Here I have written the pressure as P1 equal to 0.1 MPa. Now the pressure is converted from MPa to kPa, that means megapascal to kilopascal, using this conversion formula, right? Because later when we find out the work for the compressor or turbine work or heat supplied, uh, it will be convenient for us to find out the work or the heat in terms of kilojoule if the pressure is in kilopascal, right? Otherwise, we need to do some multiplication factor. We have to include those multiplication factors. So to avoid that, we convert the pressure from megapascal to kilopascal. Next, the pressure ratio is 6.25. Normally, in the Brayton cycle, we use the notation RP for pressure ratio. So it is written that RP is equal to 6.25. The maximum temperature is 1073 Kelvin. In most of the cycles we study in thermodynamics, the maximum temperature of the cycle occurs at the state 3. That means at the end of the heat addition process 2 to 3. Therefore, the given maximum temperature is written as T3 equal to 1073 Kelvin. Then the turbine and compressor efficiencies are each 80%. It is given like this. Now, when I write these efficiencies, I use the notation for turbine efficiency eta T and compressor efficiency eta C, both are equal to 0.8. I have written all the data given in this question. Now, you should know that what are the things we need to find out. So here it is clearly given at the end of the question. Find the compressor work per kg of air, then the turbine work per kg of air, then the heat supplied per kg of air, and finally the cycle efficiency. So when we find out the compressor work or the turbine work or the heat supplied, we can assume that the mass or the mass flow rate is 1 kg or 1 kg per second, right? And additional information regarding the Brayton cycle is here, given here, pressure ratio, we use the term pressure ratio. Here it is given as 6.25. Normally, we define the pressure ratio as P2 upon P1 or P3 upon P4. That is the pressure in the process 1 to 2, ratio of pressures in the process 3 to 4. Right. So in addition to this, I have also shown the cycle or the process of the cycle, Brayton cycle, on TS plane or TS diagram. Right. So here, if you look at the process 1 to 2, that is compression, and the process 3 to 4, that is expansion, I have represented these two processes in two different ways, like 1 to 2 and 1 to 2 dash. The meaning 1 to 2 represents the actual compression process. Let me write down here 1 to 2 represents actual compression process. That means the process is non-isentropic, that means irreversible adiabatic. Then I have also represented 1 to 2 dash, which represents isentropic compression process. Similarly, if you look at the process 3 to 4, that is expansion process, you look at here, I have used two lines, a vertical line 3 to 4 for 3 to 4 dash, representing the isentropic expansion, and orange color line 3 to 4 representing actual expansion. Right. So why we represent the compression and the expansion process in this way? Because if you look at the data given, right, earlier we wrote down the given data. So we wrote two terms like eta T and eta C. What are those terms? Those are the efficiencies of turbine and compressor. Am I right? Right. So let me complete this. 3 to 4 dash is representing isentropic expansion process. Okay. So let us discuss further why we use these two representation, right? 1 to 2 and 1 to 2 dash. So the reason is, in the question they have given the efficiency terms, turbine efficiency and compressor efficiency. So these efficiency terms are otherwise called as isentropic efficiencies. Okay. So this isentropic efficiency actually relates the enthalpy change during isentropic process and enthalpy change during a non-isentropic or actual process. For example, if you take the compression process 1 to 2, right, the isentropic efficiency of compressor, that is eta C, can be written like this. I'll write here. So eta C can be written as the enthalpy change, that means delta H, during the process 1 to 2 dash, right? 1 to 2 dash. That means isentropic compression process divided by delta H during the process 1 to 2. That means during non-isentropic process. Okay, so in this way, I can define the isentropic efficiency of compressor. So how we get this expression eta C in terms of temperature? If I replace the H's, here in the numerator you have delta H and denominator also you have delta H. If I replace each H with Cp times temperature, right? And if I cancel out all the Cp's, because we assume that the Cp's are constant, right? Being the perfect gas, air being the perfect gas, right? I will get this expression eta C is equal to T2 dash T1 divided by T2 minus T1, right? So then I can rearrange this expression to get the expression for T2, which is equal to T1 plus T2 dash minus T1 upon eta C, right? So we can use this expression to find out T2, and here we are accounting for the efficiency of compressor. Similarly, I can define the turbine efficiency in this form: eta T equal to T3 minus T4 upon T3 minus T4 dash. Rearranging this expression, we can write T4 equal to T3 minus eta T times T4 minus T4 dash, right? If you look at these two expressions, expression for T2, expression for T4, right? On the right hand side, we have three terms. For example, T2 on the right hand side, T1, T2 dash, and eta C. Out of these three terms, two terms like T1, eta C are given in the question. T2 dash is unknown. So we need to find out. Let us look at T4, equation for T4, right hand side. There are three terms again, T3, eta T, and T4 dash. Out of these three terms, T3 is given, eta T is also given, the unknown is T4 dash. So here we need T4 dash. How we are going to find out this T4 dash or T2 dash? Right, so I have given the expressions for T2 dash and T4 dash here, right? So how do we get these expressions, right? So we have seen the TS diagram. I have shown the isentropic process 1 to 2 dash. Similarly, isentropic process 3 to 4 dash, right? For any isentropic process, I can relate the temperature ratio and pressure ratio like here. So for example, for the process 1 to 2 dash, I can relate the temperature ratio, that is T2 dash by T1 can be related to the pressure ratio during the same process in this form, to the power gamma minus 1 by gamma, right? So you should be careful that the pressure at 2 P2 or pressure at P2 dash, okay, both are equal because this is a constant pressure line. This green line is a constant pressure line. You can look at clearly that the point 2 and the point 2 dash are lying on the same constant pressure line. That means P2 and P2 dash both are equal. So for the isentropic process 1 to 2 dash, the temperature ratio and pressure ratio can be related in this way. So from this I can get T2 dash equal to T1 times RP. What is RP? RP is P2 by P1. So instead of P2 by P1, I can write RP here. So RP to the power gamma minus 1 by gamma. Similarly, when I write the isentropic relation for the process, isentropic process 3 to 4 dash, I'll get T4 dash equal to 3 times 1 by RP to the power gamma minus 1 by gamma. So let us look at how to use these equations, that is equation for T2, T4, then how we are going to find out T2 dash and T4 dash, right? So here I have shown the calculation part, right? So here I have calculated T2 dash using the isentropic relation. On the right hand side we have T1, RP and gamma. Gamma is equal to 1.4 for an isentropic process. So upon substituting all the known values, I get the value of T2 as 506.42 Kelvin. And next I use the expression for T2. Here I substitute the values of T1, T2 dash and eta C. Then I get the value of T2 as 558 Kelvin. Then I move on to calculation of T4 dash. This is an isentropic relation. Again, I substitute all the known values on the right hand side. Simplifying, I'll get T4 dash equal to 635.63 Kelvin. Then I move on to the calculation of T4. So in this I substitute the values of T3, eta T and T4 dash. Simplifying, I get T4 equal to 723 Kelvin. Okay. Then we come to the terms which we need to find out actually in this question. Right, in this question, we need to find out the compressor work, turbine work, heat supplied, and cycle efficiency. Right, so when we find out compressor work or turbine work or heat supplied, assume the mass is 1 kg. Right, right. So I can write the compressor work WC as the difference between the enthalpy during the compression process 1 to 2. So that is H2 minus H1. I can rewrite H in terms of Cp and T. So H2 can be written as, for example, H2 can be written as Cp into T2 and H1 can be written as Cp into T1. So Cp is common, I can take out Cp, then I'll write Wc equal to Cp into T2 minus T1. Right, in this expression, Cp is the specific heat of air at constant pressure, Brayton cycle. The Brayton cycle being the air standard cycle, I'll take the value of specific heat of air. So upon substituting all the known values, I get the value of Wc as 259.29 kilojoule per kg. Then coming to the turbine work per unit mass flow, Wt equal to, again, enthalpy change during the expansion process 3 to 4. Right, as earlier, H3 can be written as Cp into T3 and H4 can be written as Cp into T4. Therefore, Wt comes out to be Cp into T3 minus T4. Upon substituting all the known values, I get the turbine work to be 351.75 kilojoule per kg. Then heat supplied per unit mass, Qs, which is equal to Cp into T3 minus T2. Again, once again, the heat supplied is also equal to the change in enthalpy during the heat addition or heat supply process 2 to 3. So which can be written as Cp into T3 minus T2. Upon substitution and simplification, I get the heat supplied Qs equal to 517.57 kilojoule per kg. And finally, I will write the cycle efficiency in this form. For any heat engine cycle like Brayton cycle, I can write the cycle efficiency as the ratio between the net work output during the cycle and the heat supply. So here the net work output is the difference between turbine work and compressor work. Turbine work is the positive work because it is the work done by the system, and compressor work is a negative work because it is the work done on the system. So therefore, substituting the work transfer for turbine, compressor and heat supplied Qs in this expression, I get the thermal efficiency of Brayton cycle to be 0.178, or it can be written in terms of percentage as 17.8%. I hope this explanation is clear to everyone, and we will continue our discussion on problems like this in the forthcoming classes. Thank you.